Video Lecture 9D, Exceptions to the Noble Gas Rule. We have used the noble gas rule to show how molecules form. Molecules allow for nonmetal atoms to have an octet of electrons around them, or have a noble gas configuration, by sharing electrons with other atoms. We can draw Lewis structures to show this. And Lewis structures are a very powerful tool in representing the connectivity, or how atoms are bonded to one another in molecules. However, there are some cases where the octet rule doesn't quite work. One such example are molecules with an odd number of valence electrons. Our Lewis structures and the noble gas rule seems to imply that all electrons must pair up. We see that electrons are shared in pairs, usually 1 to 3 electron pairs between two atoms at a time. Even the unshared electrons exist as lone pairs. Therefore, having an odd number of valence electrons does not work well with the noble gas rule. One such example of a molecule with an odd number of valence electrons is nitrogen dioxide. NO2 has a total of 17 valence electrons. Therefore, we expect there to be a lone electron on one of our atoms. It's customary to put that lone electron on the least electronegative atom. In this case, it's on the nitrogen atom. This leaves nitrogen with 7 electrons surrounding it. Therefore, it lacks an octet. This is often the case with odd electron molecules. Molecules, as well as atoms with odd numbers of electrons, are often also referred to as free radicals. Free radicals are common pollutants and are often carcinogenic. This is simply because odd electron species are quite reactive, as they try to obtain a noble gas configuration for one or more of its atoms. Another example of types of molecules that may lack an octet are molecules that contain either group 2 or 3A atoms, most notably beryllium atoms or boron atoms. These two types of atoms often have bonding patterns that make the central atom lack an octet. One example is boron trifluoride. If we draw a Lewis structure for boron trifluoride, as shown in the bottom right-hand side of the screen, we see that each fluorine atom has an octet of electrons. However, boron lacks an octet. Boron has only 6 valence electrons surrounding it. This is very usual for boron-containing compounds. As with the example of an odd electron molecule, having an atom that lacks an octet makes the molecule very reactive. Boron trihalides, as well as boron trihydrides, are extremely reactive, as each boron atom tends to want to gain a pair of electrons. You'll learn more about these types of reactions in your further chemistry courses. Our third type of exception to the octet rule are molecules that have one or more atoms that can have more than an octet of electrons around it. This is often referred to as an expanded octet. It is important to note that elements in rows 1 and 2 cannot have more than 8 electrons surrounding it. This is because these atoms are very small in size, and do not have the space for more than 4 electron pairs at any given time. However, atoms in row 3 or below can accommodate more than 8 pairs of electrons. This is also known as hypervalency. Sometimes an explanation is given that these atoms have d orbitals that are empty and available to accommodate extra electron pairs. But be wary of this explanation. Since electrons are considered to be the orbitals, there really is no such thing as an empty orbital. The orbital doesn't exist unless an electron is occupying it. It is easier just to say that larger atoms can accommodate more electron pairs. And this occurs for elements that are in row 3 or below. It is also important to note that our systematic method for drawing Lewis structures often fails for molecules that violate the octet rule. This includes hypervalent atoms, hypervalent molecules, odd electron molecules, and molecules containing at least one atom that will lack an octet. We therefore must use some chemical intuition to draw their structures. That is, we should look at regular bonding patterns for atoms, such as the fact that less electronegative atoms are in the center of a molecule, and that atoms such as hydrogen and fluorine tend to only form one bond with one other atom. In the next part of this video, we will look at the Lewis structures for sulfur hexafluoride and the triiodide ion, which will illustrate these points. We will now look at 2 examples of molecules that contain one atom that has an expanded octet, or more than 8 electrons surrounding it. One such example, and a common one at that, is the sulfur hexafluoride atom or molecule. To begin, we will add up the total number of valence electrons, something that we should always do when drawing a Lewis structure. Again, this is because this is the total number of electrons that should be represented in your Lewis structure. Sulfur has 6 valence electrons. Each fluorine atom has 7 valence electrons. This gives us a total of 48 valence electrons. Now, to show you that our systematic method fails for molecules containing an atom with an expanded octet, we'll do our second step. That is, we will count up the total number of electrons each atom would have if it were isoelectronic with a noble gas. We have a total of 7 non-hydrogen atoms, so we will multiply 7 by 8, which is the total number of valence electrons that each noble gas has. This gives us a total of 56. We'll combine steps 3 and 4 from our systematic method. That is, we'll subtract 48 from 56. Which gives us 8 shared electrons, and divide this by 2 to get the total number of bonds. So we get that our Lewis structure should have 4 bonds. This is way too small. For the number of atoms that we have in sulfur hexafluoride, 4 bonds is not an adequate number of shared electrons to ensure that all atoms at least have an octet of electrons. So this is a case where we should use our chemical intuition. To do this, we will first follow a rule that the most electronegative atoms should go in the center of the molecule. The less electronegative atoms should go in the center of the molecule. Sulfur is less electronegative than fluorine, so we will place it in the center of our molecule. and we're surrounded by the fluorine atoms. We do this because fluorine only forms one single bond at one given time, and therefore tends to act as a terminal atom. We'll begin by drawing one single bond between the sulfur and each fluorine atom. We've so far used 12 electrons and have 36 left to use. We'll use those 36 electrons to make sure that each fluorine atom has an octet of electrons. We've used up all 48 electrons, and all of our fluorine atoms have an octet. All row 2 elements should at least have an octet of electrons around them. Sulfur, which is in row 3, has 12 electrons around it, which is perfectly fine for a row 3 element, since it is able to expand its octet. Our second example of a molecule that is able to expand its octet in one of its atoms is the triiodide ion. Which is I3-. Once again, we'll count up the total number of valence electrons in this atom, or molecule. There are 3 iodine atoms, each with 7 valence electrons. We also have a -1 charge, so we should add 1 electron to our valence electron count. This gives us a total of 22 valence electrons. Once again, we'll use our systematic method only to show that the method fails for such a molecule. Since we have no hydrogen atoms and only 3 non-hydrogen atoms in this molecule, we'll multiply 3 by 8, which gives us a total of 24 electrons needed to satisfy the noble gas rule for each atom. We'll combine steps 3 and 4 once again. So we'll subtract 22 from 24. This gives us 2 shared electrons. If we divide that by 2, that would give us 1 bond. Once again, this is far too few bonds to draw on our Lewis structure. Since there are 3 atoms in the molecule, we at least need 2 bonds. So how do we tackle this Lewis structure? We start by arranging all the iodine atoms in a row. Because iodine is in group 7A, we'll start by adding 1 bond between each set of iodine atoms. This allows us to use up 4 of our electrons. We'll then continue by adding enough electrons around each iodine atom so that each has an octet. So that means that on the terminal iodine atoms, we need to add 6 electrons. And 4 electrons on the central iodine. We've now used up 20 of our 22 electrons. The extra pair of electrons is generally added to the central atom. So we'll add it to the central iodine atom. Iodine is in row 5. Therefore, it is able to expand its octet. So it's okay that we have a total of 10 electrons around the central iodine. We complete our Lewis structure by placing it in brackets and putting the charge, -1, in the upper right-hand corner. This is an example of how we can use our chemical intuition and some of the rules that we've learned about Lewis structures to draw appropriate Lewis structures for molecules with atoms that can expand their octet.